Hello all, welcome back. So in this video, we will try to understand. I started early morning, try to launch this mission and one anomaly observed during the stage three. So we will try to understand from the graphs. So all right. So this is ISRO. They told that 18 May 2025. This was a 101 launch was attempted. PSLV C61 performance was normal till second stage. Due to observation in third stage, this mission could not be accomplished. So let us try to understand some overview. What's the objective of this mission and how? Okay, so India is said to achieve a significant milestone with this. This was a mission 101 of its space program. So 18 May 2025, 5:90 5:59 so AM Indian Standard Time is to be launched. So this is a satellite EOS-09, the Earth observation satellite. Brought the this launch vehicle PSLV C61, and this is from the first launch pad in Satish Dhawan Space Center, Shore. And this mission will place the Earth observation satellite into the Sun synchronous polar orbit. This also in shortcut we can say ASSPO. We will understand what the Sun synchronous polar orbit. In case of observation, Earth observation, Jallevi satellite is placed to in this orbit. Okay, and this is launch vehicle details. This is 63 flight of the Polar satellite launch vehicle, and 27th using the this is like version large version we can say PSLV XL configuration. So this is like details. Height 44.5 meters, lift of mass 321 tons, configuration 4 stage with the 6 solid straps on booster. Okay, we will not go more details. Our this video will focus on the how would know the anomaly observed from the graphs. Okay, and what is the probable possible reasons to for this problem actually. All right. So after EOS-09 is deployed, orbit change thrusters will be used to reduce the altitude of PS4. This is a stage 4. Okay. So this concept we are using in case of reduce the altitude. All right. So let us understand what is a polar orbit. So polar orbit is a orbit where the satellite travels from roughly one pole to other. That's why we call polar orbit. Typically at a low altitude, 200 to 1000 kilometer. Okay. So there is a type of satellite orbit that passes over the Earth poles. Okay. So if you combine Sun synchronous polar orbit, Sun synchronous orbit is also a particular kind of polar orbit in which satellites are synced with the Sun. Okay. So matching Earth rotation around the Sun, they always appear in the same position related to the our star. Okay, there will be no relative motion. So this means they pass over the same spot on Earth at the same local every day. Okay, so that's why we are using the synchronous polar orbit. So this is ideal for consistent lighting condition. Okay, that's why we are placing and we choose this kind of orbit. So you can understand, you can visualize here this like north and south pole. So this our equator, this here this like this orbit is called the sun synchronous polar orbit. So near to north and south pole. Okay, so these are key characteristics. Inclination 90-degree, altitude commonly between 500 kilometer to 1000 kilometer. This is like a low Earth orbit to, okay, and orbit path nearly perpendicular to the equator. Of course, this is a pole, so passing to pole, so this is a perpendicular to equator. Satellite passes over the different longitudinal slices of the Earth with each orbit. Coverage over time, the Earth entire Earth surface can be observed. That's the importance. So, in case of this polar orbit, Sun-Sun's polar orbit, but the observation, but the application point of view. So, in case of if you want to observe the Earth in terms of environmental monitoring, climate data collection, natural disaster assessment, remote sensing, surveillance, meteorology, weather satellites, mapping, and cartography. So, in this kind of application, generally we use this orbit. Okay. So, advantages like global coverage, every part of Earth becomes visible over times as the planet rotates beneath the satellite orbit. Okay, so high revisit rate useful for monitoring dynamic Earth processes like deforestation, ice melting. So for this very complex, such kind of application, this is like advantage we can see actually. So one more thing, consistent lighting. So sun's Cornerstone variant enables image comparison over time. So what are disadvantages actually? If you choose this orbit, high launch energy requires more energy to reach polar orbit from typical launch sites, which are often closer to the equator. Not ideal for continuous communication. So in case of communication satellite, we have to go for geostationary orbit. So polar orbit only applicable for, only useful for observation kind of this kind of application you can see. All right. So based on the application, we can choose the which orbit is suitable. Okay. So then we move on the our satellite specifications. So EOS-09, EOS, this is full form is Earth Observation Satellite, is designed to provide continuous and reliable remote sensing data for operational application across various sectors. Okay. So key feature payload like synthetic aperture radar we are using here. Launch mass uh, 1696.24 kg. Mission life 5 years. Okay. After this, it will be deorbit and deactivate in the atmosphere. Okay. So sustainability includes deorbiting of fuel for safe post mission disposal. Okay. So we have to avoid the debris. So here you can see this is our site, launch pad. So our mission is ready to, launch. So everything was fine. You can see here proper things going initial time. You can see in this video, sorry, in this image. All right, everything was fine. So here you can see this like our real-time animation. They try to understand here. So I think this is second stage. Okay. So everything was fine here also. So everything was going smooth. You can see here. Now in this flight parameter here we can understand like here you can see our right hand side. This is like yellow part saying T is tells a tracking, I is instrumentation. So tracking means like in a ground station we have setup, tracker setup like radar or proper setup there. Generally we use like in our India, first we use the SAR and then we go Trivandrum, then Mauritius. So they are station, okay. So we have to track from where system is there, okay. And second is instrumentation. This is green. They are telling green actually part. So instrumentation like generally in mission they keep the OVC onboard computer. So in this navigation inertial measurement unit, based on their real time, they try to compute the data. There are a lot of data over there, and they in case of closed loop guidance, and we can say GNC part, like guidance navigation control system, they try to they try to use the data, and by own they able to take a decision and try to maintain the track trajectory, whatever intended mission, whatever intended path, we can say it try to maintain actually. So here we understand that in our x direction, x this is time in second, and by there are two parameter they are mentioning, one altitude in kilometer and relative velocity kilometer per second. So here you can see this is a starting, this is like here two value there, one is a green and second one is yellow. So green is a coming from instrumentation. What does it mean actually? Like in our onboard computer using the inertial measurement unit, like like gyroscope, all sensor there, inertial measurement unit, accelerometer. So for this inertial measurement unit system, onboard computer using the telemetry, they try to send the data to the ground station. Okay, and we are do the plot actually here. And second is a tracking. So tracking means from ground station, like tracker, like radar system, they try to track it. And here you can see from zero start initial, it is overlapping, so everything was fine. And this white curve, you can say this is like expected velocity profile. Okay, so initial this was fine, and the second one is you can see this one is our altitude, you can see is try to achieve the altitude. Okay, so over time our altitude will be increased. So and you can see our right hand side this is ranging. If you put perpendicular here, and if you measure this distance, it's called the range from the launch pad, you can see. Okay, and from here this altitude was 140 9.4. Okay, and time was it 181.8. So all stages, like sequence it has some finite time to complete this stage. Okay, then second this time was 200 112.8 second. Here you can see also, and the tracking data and our instrumentation data coming from OBC onboard computer is coming proper, you can see perfectly matching. Okay, and whatever our expected velocity profile is try to track it. Okay, so in case of tracking there is no control loop, there is no loop at all. Okay, simply we are supervising, we can say simply we are tracking from our ground station. Okay, but in case of instrumentation, this in this our closed loop guidance involved based on the inertial measurement unit and navigation system. Okay, so all right, so here everything was fine. Here you can also, after reaching the time 319.8 second, here also everything was fine, try to track it. And data from instrumentation, data from system, I mean onboard computer, and tracking done by ground station is perfectly fine. And here also when we achieve time 361.8, here also it is fine. And then now our situation going normal, you can see here. Okay, so this instrumentation tracking is yellow. Okay, and instrumentation try to divert here. Okay, so our you can see maybe before 2 seconds before, maybe because I capture this photos from live live video telecast by ISRO official. So and then here you can see visually, you can understand that it gets diverting, it's not is not overlapping. Okay, so this problem is over there after 378.8. Okay, and perfectly you can see it's going downward here. Okay, 382.8 second, and this my data you can see here. So ignition stage 3 also 262.9 second. So they also, I think, stage 4 engine start also there. They put mention this time also 506 second. And here you can see this complete graph. Usually we can understand everything going, abnormal condition. This is normally observed. So our estimation data saying that this velocity should be there, and tracking is showing like that. This is not same actually, and whatever our expected graph is not tracking actually. Okay, so this was a problem actually. So you can see here, and after this they awarded rates actually, they awarded this mission. So anyway, our actual data, ISRO, they have a lot of data, mm, you know ample data they have, and they try to understand what's the problem was there actually here. Okay, because in case of instrumentation they are based on our real-time data. They try to compute, and they send the data to telemetry, through the telemetry in ground station, and this data is not matching. Okay, so that's why this problem, this anomaly observed. Maybe some, there are a lot of algorithms was there in GNC, and so maybe some, they feel some misinformation, but what is the actual things is something different. Okay, so this was a problem actually. So here you can see our healthy point of view, it should follow this white line. You can see it should follow this line actually. Okay, so this time was I think this time is 754.5. That time I captured this actually. Maybe some before I think this problem observed. Okay, so what happened during the launch? So you can say first stage, this is solid booster, performed properly, performed normally as usual. Second stage, liquid engine, also successful. Third is solid rocket motor. This anomaly occurred here. Okay, and fourth stage, liquid, not ignited due to the earlier failure. So maybe third stage anomaly, maybe like chamber pressure dropped unexpectedly and during the third stage ignition, and this abnormal pressure drop means the rocket lost thrust midway through its trajectory. As a result, the vehicle failed to attain the velocity and altitude required for the orbital insertion. So that's why ISRO manually aborted the mission before the fourth stage was ignited to avoid space debris and potential damage. Alright, so that's why. So what is the outcome of for this actually? So EOS-09 did not reach orbit. Satellite eventually re-entered the atmosphere and was lost. The PSLV C61 mission was declared a failure. Okay. So what is the significance of this mission actually? Loss of strategic satellite. EOS-09 was imperative for civilian and military purposes, especially real-time imaging and terrain mapping in difficult conditions, crop yielding estimation, border surveillance, natural disaster management. All right. Technical and investigative aspects, root cause analysis. ISRO has constituted a higher level failure analysis committee to examine telemetry, pressure, and thermal data for launch. They will they will start, understand what's the problem actually. Telemetry, pressure, thermal data. They will try to understand, analyze structural integrity and propellant performance. So they will also try to what the issue was there, whether the design based issue, manufacturing related issue, or procedural based, and probable causes, nozzle erosion or damage. improper grain burning, you know, solid propellant. Okay, like whatever, how much amount of fuel, you know, need to burn, maybe proper burning not happen, that's why proper thrust not be, you know, produced actually. Seal failure in pressure containment system, so defect during assembly and integration in solution layers. Okay, so